that we need to understand is that electricity and magnetism
Chapter 4.
are linked. They work together, right? You can't really have one without the other. Okay? Electricity and magnetism go hand in hand. So we describe this as the phenomenon of electromagnetism. Now, magnetism is defined as the ability to attract a material such as iron, cobalt, or nickel. Okay, so basically, right, if you think about a magnet, right, magnets are attracted to, or they attract iron, right, or steel, okay, things like that. If you have a kitchen magnet, right, sometimes the kitchen magnet will stick on certain things, sometimes it won't, right? Now, magnetism is a fundamental property of matter. It's like mass, it's like electrical charge. So whether or not a material is magnetic, right, is something that's part of the material's identity in a way. Okay? This is a physical phenomenon which arises from the force caused by magnetic fields that attract or repel other objects. So magnetism exists due to magnetic fields. Magnetic fields come out of an object and they interact with other objects, and that causes the attraction or potentially repulsion. A magnetic field is the area around a magnet, a magnetic object, or an electric charge in which a magnetic force is exerted. Right? So do notice that not only does a magnetic field come from a magnet, but it can even come from an electric charge. Because once again, right, concept of electromagnetism, electricity and magnetism are somewhat linked. So I've got a really cute little GIF up here, right, of some examples of how magnetism can work, right? Now, as far as like this iron, cobalt, nickel thing goes, we are talking about like their pure elemental form. Right? If you get something that's only like partly cobalt or partly nickel, right, like a 5-cent coin, that's not really going to be magnetic. Okay, so don't think that you can have a magnet and pick up, Thomas Jefferson, right? Because the nickel is not really magnetic. Yes.
Do magnetic fields have anything to do with like thermal energy at all?
Do they have anything
Like-
to do with thermal energy?
Like if they speed up the electrons enough or whatever the electric field, would that have some effect on like would those magnets start to spin and heat up essentially
So
outside of friction?
outside of friction. That is possible due to the fact that, once again, this is electromagnetism. Because if you have a changing magnetic field, you will induce an electric current. Electric currents run into resistance, and when you have resistance, you produce heat. So yes, you are capable of hitting an object with magnetic fields.
So is that why when you go into an MRI, it feels like stuff is burning or like tattoos or?
That is part of the reason. Yes. Any other questions? Okay. So just some vocabulary here. We have this concept of the magnetic dipole. Okay. And even though it sounds really fancy, right? You notice that there's the word pole here. And when we talk about magnets and poles, what comes to mind? If you talk about a magnet and the poles of a magnet, what comes to mind?
North and south.
Like the positive.
Positive and negative.
Right, so positive and negative, or north and south, right? The north and south poles. For example, the Earth has north and south poles, correct? Why? Because the Earth is essentially a giant magnet. Right? So it's got a north pole, it's got a south pole. Same thing for your magnets. Magnets have a north pole, magnets have a south pole. And this goes from something as big as the Earth all the way down to something as small as an atom. Even atoms have magnetic dipoles. They have a north and they have a south, as long as the atom is magnetically active. Okay, so kind of going back to what Jay was talking about earlier, when he mentioned MRI. How does MRI work? It's because the hydrogen atoms inside your body are magnetically active. The hydrogen atoms in your body have a north pole, they have a south pole. They act like miniature magnets, and so we're able to manipulate those magnets to create images. Now, a single atom, right, is very small. You're not really going to see much of an effect from a single atom. But as it turns out, atoms that are near each other, atoms that are in a group next to each other, all tend to have the same magnetic properties. So instead of just talking about a single atom, more often than not, we talk about groups of atoms called magnetic domains. In magnetic domains, all the atoms inside there just have the same dipole pointing in the same direction. Right? So as you can see, within these different magnetic domains have dipoles pointing in different directions, right? These arrows are representing the dipoles. But within each magnetic domain, all the arrows are pointing the same way. Okay, so overall, right, the magnetic dipoles or the magnetic fields are pointing in different directions, random directions. But inside the domain itself, right, they're all in the same direction. So we can kind of just group them together.
What did you say was pointed in different directions?
So these arrows, these represent like the north poles,
Okay.
right? In other words, this is the direction the magnetic field is pointing in.
So it's different directions.
Correct. So you can see they're pointing in different directions, but if you're only looking within a domain, right, everything in the domain points the same direction.
Okay.
Everything in the domain acts the same way. Yes?
So that whole thing is a magnetic dipole, and then
So each arrow is a magnetic dipole.
each arrow.
Right? Each section is a magnetic domain. The entire thing is just an object.
Okay.
Okay, so in this case, this could be like your body. Right? Your body is made of many magnetic domains. Right? The magnetic domains are all pointing in random directions. That's why your body's not magnetic, right? That's why you can't lift yourself up with a magnet. But if you look close enough, right, look at a small enough piece of your body, you'll notice that all the magnetic fields are pointing in the same direction. All the magnetic dipoles are pointing in the same direction. So that makes up your magnetic domain. Now, where does magnetism come from? What determines if an atom is going to have a magnetic dipole or not? For this, we need to look at the electrons of the atom, right? The electrons need to be spinning in one direction. Okay, not the band, but in just the same direction. So, how does this work? How do electrons spin in the same direction? To answer this, we need to just look at the outside shell of an atom. What is that outside shell called? Valence, very good. How many electrons fit on that outside shell? Good, you can fit up to 8 electrons on that outside shell. Now, there's a really interesting property of atoms when you try to fill that outside shell with electrons. If you put one electron into the outside shell, it's going to point one way. We'll call this, it's going to point up. If you put a second electron into that outside shell, it ends up pointing down. Okay, so they cancel each other out. But then for your next 6 electrons, you put a third electron in, up. A fourth electron in, up. A fifth electron in, up. They happen to all end up pointing in the same direction as you fill this shell. So, depending on the number of electrons you have, that'll determine whether or not you have an equal number of up and down, or if you have some excess, some leftover ups that will form your magnetic dipole. If you keep adding electrons, if you add a sixth one, now it's going to be down. It cancels out one of them. Add a seventh one, it cancels out the other one. Add your last and final eighth one, it cancels out your final up electron, and then you have 4 pairs that are up and down, right? And then no more magnetic dipole. So it all just has to do with the number of electrons in that outside shell, that valence shell of your atom. That is where magnetism comes from. Yes?
So is a domain just a bunch of electrons? Is that what that means?
So the electrons determine your dipole, and a domain is a whole bunch of dipoles.
Okay.
Mhm.
So many electrons is dipole, many dipoles domain?
It doesn't have to be many, but the electrons determine if you have a dipole. So as far as the electrons go, the outside shell will have 4 up and 4 down maximum. But if you don't have all 8 electrons, right, you can take away some of these, it fills the ups first, basically. So as you're filling it halfway, it fills the ups first, and then afterwards it fills in the downs, the ones pointing downward. So your dipole, right, will exist as long as you have some which are up. As long as you have more up than down, you have a dipole. And of course, if you do want to learn more about this and are interested in the topic, we do go over this in more detail in MRI. So once you graduate, if you feel this is interesting, feel free to join us.
He's trying to recruit already, huh?
Now, when you have something with a magnetic dipole, right, and you place it into a magnetic field, what happens is the dipoles tend to arrange themselves to match the direction of the magnetic field. And we describe the magnetic field using lines of force, which we call flux. So if you've ever seen like a magnet drawn with like these kind of like curved lines coming out of it, those are your lines of flux. And in fact, you can see the magnetic field. You can see these lines of flux if you put a magnet into a pile of iron shavings. Do you notice how these iron shavings form this kind of arch like this? It forms this kind of circular motion. That is the magnetic lines of flux. That is the direction the magnetic field is traveling in. The magnetic field travels up the North Pole here, comes around, and enters back through the South Pole. Right? So that is the direction your magnetic field is traveling in. Okay, these are your lines of flux. So you've got iron shavings. Iron shavings have dipoles. And you notice that these shavings line themselves up to match the magnetic field. Does that make sense? Okay, looks like we have a little video here. Let's see what happens. Oh,
Hold on, Mr. Phung.
okay.
So you saying that's a
La Roche
oh.
Posay Lipicard Body Cream for extra dry skin. It restores skin's barrier and provides 48-hour hydration.
Hi.
Hi there, and welcome to Mr. Musselman's online teacher workshop. Magnetic fields can be tough for students to conceptualize, but with the help of a magnet, a piece of clear glass or plastic, and iron shavings, you can be on your way to helping students better visualize the magnetic field all magnets create. Begin by placing the clear plastic or glass over a magnet. In this case, I use the cover of an old takeout tray. Carefully shake the iron filings out over the magnet and clear cover. You'll notice that as you shake, the filings will begin to arrange themselves almost magically across distinct lines. This is a result of the north and south poles of each shavings arranging themselves with the magnetic field. When done shaking, make sure kids observe the pattern both overhead and from the side. From the side, they'll observe that the field is three-dimensional, meaning the magnetic field extends in all directions from the North Pole and wraps back around to the South Pole. Consider trying this activity with a horseshoe or ring magnet to see how the fields are different than the bars. With the help of this activity, students should come to recognize that all magnetic materials create a magnetic field. That includes Earth's core. A diagram like this can also be used to see how well students understand that North and South poles attract and vice versa. Ask your students, why does the imaginary bar magnet inside the Earth appear to be upside down? Want to learn more? Visit us online at the Burlington Science Center.
Alright. So that's kind of a representation, right? You saw exactly how this came to be.
Mr. Phung,
Yes?
so you're saying about the lines of the direction, that's what it's called, the flux?
Correct, that is the flux.
Okay.
And we'll see some examples of lines of flux in just a moment here. Any other questions about magnetism so far?
Is it lines of force or lines of flux?
So these are lines of magnetic force. The specific vocabulary we use to describe them is called flux. Right? So you can call it flux or lines of flux. Right? But flux itself just means that it's the lines of force for a magnetic field. So you can have different types of force, right? But if we're talking about the force from a magnetic field, that is flux. Any other questions? So, as far as magnets go, what properties do magnets have? What do magnets do if you have two of them? Right, you either attract or repel. Why is that? Just kind of looking at how the lines of flux are traveling, why do you think a magnet might attract or repel? For example, right? Which way did we say the magnetic field is traveling?
North to south.
North to south, right? So it comes out this way, it loops back around, and it comes in this way, right? So looking at this, why do you think two magnets might attract each other?
The electron, the way that the electrons came in?
The way, what?
Electrons came in?
Like-
No?
So, if we look purely at the lines of flux, this is what is happening, right? So, as you can see, right, travels from the North Pole to the South Pole, right? Now, if you have two magnets, right, over here, okay, coming out the North Pole, over here, coming back into the South Pole, you notice that the magnetic field is traveling this way for the first magnet, and it's traveling this way for the second magnet. The directions match, right? It comes out towards the right on this North Pole. It's coming in from, right? The arrows are traveling in rightwards on the South Pole. So that's why these two end up attracting, because the lines of flux are going in the same direction. Right? So when they, right, if they snap together, now you just have a giant line of magnetic flux, right? Comes out the North Pole into the South Pole. Right? So these lines of flux are traveling in the same direction, and so that's why your magnet attracts. On the other hand, what if you try and put two of them two of the same pole together. So if we have north and north here, and you try and put them together, well, this north is trying to go this way, this north is trying to go this way, and they crash into each other, right? And since they're crashing into each other, they push each other away. So that's why you can't put two north poles together, because the lines of flux are going to push in opposite directions. Yes, Jay?
So the attracting force will always be traveling from the south pole to the north pole, whereas the force that's being attracted is north to south? Is that how I'm understanding that there?
Say that one more time.
So which one in the diagram up on top would you say is like the one that's actually attracting?
Both of them are doing the attraction.
Then what's the sign on the right? The little Greek.
This thing?
Mm-hmm.
That is a theta. That is I believe that's the symbol used for lines of flux.
Oh, okay. So that's not saying like this one was a little weaker, so it got pulled in.
Correct.
Or, okay.
Mhm. So yes, this is just a symbol for lines of flux, if you use it in an equation or something.
Then on the like test question or whatever, how would you word the top one as a test question, like same direction?
How would I word it, or how Ms. Bonilla?
How would you word it? Because Miss Bonilla would be nicer.
Okay.
Okay.
So, I mean, I'll probably just ask you something like, okay, if you've got two magnets, right? Which of these combinations, or putting which of these poles together would cause the magnet to attract or repel, perhaps?
So south to north, north to south.
Mhm. Maybe it would be like a choose more than one, right? And I'd have to give you a couple different things like north-north, south-south, north-south, south-north, right?
But you wouldn't incorporate inside and outside the magnet.
So I could ask you something like, which way do the lines of flux travel outside the magnet? Or which way do lines of flux travel inside the magnet? Right, so outside the magnet, right, it's traveling from north to south. But of course, right, it doesn't end here, it's a loop. So it loops back in, but while it's inside the magnet, right, it's traveling from south to north.
Oh, so those are the ones that just aren't shown.
Right, so we're not showing the lines inside, but yes, these lines do travel the rest of the way across. It is a full oval. Now notice, right, this attraction or this repulsion only works if the object has lines of flux. If your object does not have lines of flux, right, if it's not magnetic, then it won't be attracted, right? Then this won't happen. By the way, have we figured out why we call these dipoles?
Because there's two of them.
That's right, because di stands for two, right? You have two poles, one north, one south. If you take this magnet here and you chop it in half, do you only have a south pole remaining?
No.
What happens if you chop this magnet in half?
One would become north.
That's right. This end will still be your north pole, it's just going to be shorter. You always have a north and a south pole. Any questions about this so far? In that case, this brings us to the laws of magnetism. Every magnet has a north and south pole. Okay, we saw that. Right, so even if you chop a magnet in half, you're still going to have a north and south pole on each half. Like poles repel, opposite poles attract. Right? We just saw that. If it's north and north, right, you're going to repel each other. But if it's north and south, they're going to attract each other. And finally, the force of attraction is directly proportional to the strength of the poles and inversely proportional to the square of the distance. Right. Where have we seen something similar to that? I think I've heard
Your
it.
class?
In my class?
And Miss Reynolds.
Yes.
Hmm.
Well,
So-
yeah, and her, so, yeah. Part 1 of chapter 4.
Did you talk about Coulomb's law in Miss Bonilla's class earlier?
Yes.
Yes.
Mhm.
Yes, you did, right? With charges, right? Not with magnets, but with charges, right? Electrical charges. Right? But like we said, electricity and magnetism are very similar to each other, right? They're connected. Three laws of magnetism.
The previous slide, did it say, I thought it said, light poles attract, I believe it was opposite.
So,
Opposite direction repels, same direction attracts.
Opposite direction of the lines of flux.
yes. And so the lines of flux are traveling in opposite directions like this. So similar poles, lines of flux are going to be going in opposite directions. So yes, sorry, this is specifically talking about lines of flux. If you need to make a note of that, just so you don't get confused. Keep an eye.
So that was only in terms of flux.
Correct. So this here is in terms of flux. Right, so we're talking about direction, right? Not poles, but direction.
So light poles repel because the lines of flux are going in opposite directions.
Correct. Okay, are we okay to move on? Anyone still writing? Alright, so when we're talking about magnetism, there are two possible units we can use, but the most common one is Tesla, right? Not the car, but the unit. Named after physicist Nikola Tesla, who was kind of a rival to Thomas Edison back in the day. Tesla believed in alternating current. Thomas Edison believed in direct current. In the end, we have both. Right? But yes, they used this name for the unit of Tesla. Now, if we're working with really, really, really small magnetic fields, we instead have a unit called Gauss. Okay? But usually you're going to be seeing the term Tesla. To get an idea of how big a unit of Tesla is, most MRI machines are somewhere between 0.5 and 3 Tesla. Okay, so here at Harris Health, we have, I think, 1, 2, 3. We have 4 machines that are 1.5 Tesla, and we have 2 machines which are 3 Tesla. And then, like we said, materials can react to magnets in different ways, right? They may be attracted, they may be not attracted. So if they are not attracted, right, we call those non-magnetic. Something like wood, you don't expect a piece of wood to be attracted to a magnet. Diamagnetic, these are actually materials that have minor repulsion to water. If you actually get a strong enough magnet, you can actually kind of push water away using a magnet, because water is diamagnetic. Paramagnetic is something with a slight attraction, right? So dia is slight repulsion, para is slight attraction. Okay, so this is something like aluminum, platinum, or the contrast we use in MRI, gadolinium. Okay, so if you have a tin can, right, you've got a soda can. A soda can's not going to be very strongly attracted to a magnet, okay, but it is very slightly attracted to a magnet. And then at the very end here we have ferromagnetic. These are materials that have very, very strong attraction to magnets. Right? So iron or steel, right? Or those materials in our definition of magnetism, right? Cobalt, nickel. These metals are highly attracted to magnets. So, if you go for an MRI scan, right, you absolutely do not want to bring any of these things into the room, right, because they would be attracted to that MRI magnet. These things here, right, just minor, that's probably going to be more acceptable. Yes, Jake?
So would titanium be para or dia?
Titanium is para.
Para.
So, for example,
That's
right,
why it's safe for implants.
correct, orthopedic implants. Right nowadays, most orthopedic implants are made of titanium or some titanium alloy, and they are not ferromagnetic, which means it's not going to suck a patient's leg into the magnet, right? If they've got an implant, it's only going to be minorly attracted to that magnetic field. Now, the implant can still cause issues with the actual image itself, but it's not going to get sucked into the magnet.
So will it have like a slight pull, like when the patient's in there, will it, you know?
Mhm. So they most likely will not even feel a slight pull.
But if someone's wearing a nose ring that's made out of precious metals,
What kind of precious metals are we talking about?
let's say something like just nickel or straight cobalt.
I mean, if it's straight nickel or straight cobalt, then yes, ferromagnetic, that's going to get ripped off your
Or
nose.
like how fast is it?
It depends on the strength of your magnet and how close the patient is to the magnet.
Well, I tried nothing there.
I would like to see that.
So, no piercing.
You can see that.
I would like to see that.
Right, so that's why please do not wear any extra stuff if you do end up going to an MRI rotation your senior year. Like, you can leave all the jewelry and all that stuff at home if you're in the MRI rotation. Make sure you keep yourself safe.
Will it suck up your badge?
It will not suck up your badge, however,
It'll erase it.
your badge does have this magnetic strip here. If you wear your badge into the MRI room, chances are it will erase this magnetic strip. So, this is as good a time as any to warn you guys. Almost every year, without fail, I have this sequence of events happen. I'm sitting around in the morning, I get a phone call. I pick up. Hello, yes, this is Mr. Phung. Right? It's like, Mr. Phung, I'm at Ben Taub. I'm trying to get OR scrubs from the OR machine. The OR machine's not taking my badge. Okay. What rotation did you have before this? Oh, I was in MRI. While you're in MRI, did you wear your badge into the scan room? Oh, yeah, I left my badge on. I found your problem. Yeah, so your badge is completely white. You're not going to be able to use it on the scrub machine. You're going to have to go to security and beg them to give you a new badge. Right, good luck.
Click.
Right, so,
I can't help it.
right, so, yes, it won't. So your badge will still work in like opening doors and stuff, but that black strip, that magnetic strip, will end up getting erased if you bring it too close to a magnet. Same thing goes with your credit cards. Like nowadays, most of us use the chip on the credit cards, but if you need to use the magnetic strip, right, if you need to swipe it as a last resort, it's not going to work anymore because the magnet will have erased that information. Okay? So try and avoid bringing things too close to the MRI magnet.
Is the tap to pay thing also magnetic, or is that like a just digital feature?
That's digital. That should be okay. So let's talk about electromagnetism now. Like we said earlier, electricity and magnetism are two parts of the same force, right? They are interconnected. A moving electrical current will create a magnetic field. Right? And a moving magnetic field will create an electric current. Right? This is part of induction, right? Magnetic fields, electric fields, motion, right? They're all connected to each other. Here we have a coil of wire. When we have a coil of wire like this, we call this a solenoid. Okay, so a solenoid is a coil of wire. If you run an electric current through a solenoid, you will create a magnetic field. And the bigger your solenoid, the bigger your magnetic field. So, yes, Jay.
So this is kind of what I was talking about earlier with the thermal energy. I've seen videos of like metal being melted extremely fast because of stuff like this. Like how does that happen? Are we gonna talk about that later?
So we're probably not going to talk about that in detail in this chapter, but in this class at all.
Okay.
That'll be more of an MRI thing. But once again, remember, a magnetic field creates an electric current. If you've got an electric current in here, right, you do have resistance, you will have heating.
What was you about to say about the solenoid?
The solenoid, yes.
Yeah, you said if it increases, it does what?
Correct. So if we have a bigger solenoid, right, more loops, more coils, more turns, then we have a stronger magnetic field. And so if we look at something like an MRI machine, is an MRI machine made of just a bunch of kitchen magnets stuck together? No, right? That's not going to give us a strong enough magnetic field. How do we get such a strong magnetic field in an MRI machine? We have this type of solenoid inside our machine. Right? So if you just imagine this loop of coil, right? You just surround it with some plastic, leave the hole in the middle open, and you stick a patient inside. This is your MRI machine. Right? Just stick the patient inside the middle of this solenoid. Now, the reason we're learning about this isn't because we're learning about MRI, right? We are learning about electromagnetism because this also somehow relates to X-ray and X-ray production. So, let's talk about why this is important. First of all, principle of electromagnetism, right, discovered by Danish physicist Hans Ørsted. And you notice, right, that if you've got this conductor that carries a current, right, so you've got this coil, this solenoid with the current, it will actually deflect a compass needle, right? So you have something that's creating current, you bring a compass needle nearby, and instead of pointing north towards the Earth's North Pole, right, it will point towards the electric current, or follow the magnetic field created by the electric current. So, if we wanted to make the electric current stronger, right, we create a solenoid. If you want to make the solenoid even stronger, you can even throw an iron core in the middle. Right, so instead of just these wires surrounding air, you take an iron bar and you wrap the wires around that iron bar, and that will strengthen the magnetic field. So,
Because it's speeding up the way that the current's traveling?
so it's just helping to induce a magnetic field within the iron bar as well.
Okay.
So now the iron bar also helps to create those lines of magnetic flux. So this is right? So this is based off electromagnetic induction. Right? Once again, electricity flowing through a wire, right, induces a magnetic field. familiar. We discussed this back in PRE1. We have electricity, a magnetic field, motion. As long as you have two of these, you will produce or induce the third. So, for example, if we have our conductor, right, our wire, we turn it into a coil, right? So we make our solenoid. You stick iron in the middle, right? And then you run electricity through. You get yourself an electromagnet. If you increase the number of coils, you increase the strength of your magnetic field. Okay? If you increase the speed at which you pass a conductor through that field, you can increase the voltage. So over here, right, if we take a look, we've got a coil of wire here. Right? So we have our conductor, we have our wire, and here we have a magnet, correct? So we're moving this magnet through our wires, and notice that down here, I know it's a bit blurry, but can you tell what letter this is?
Volts, V.
V, right? V for voltage, for volts, right? You can see that as we move that magnetic field back and forth here, motion, magnetic field, we get electricity. We're getting a voltage, right? This is induction, right? As long as you have two of these, you will get the third. So something like this would be similar to how a power plant works, right? How does a power plant give us electricity? It's just using a moving magnet, right? A moving magnet. That's where the power in your plugs is coming from.
Mr. Phung?
Yes, Jay.
So what if they had like two of those tubes with the wires wrapped around it, and then they did that? Would that increase the magnetic field as well?
So if you had like a second thing over here?
No. So well, yes, but more so like let's say you have a straw.
Mm-hmm.
You wrap around wire on that, and then you get a paper towel, like the middle of the paper towel.
Oh, so you have a bigger loop of wire around
Yeah,
it.
that's what I'm saying. So like
So
another,
yes, yes, you would increase your voltage, although keep in mind that second layer is going to be farther away. The magnetic field is going to be weaker, so it's not going to have as much induction. Yes, Emily.
What do you mean about if you have two, you can induce the third? Like which two?
Of these three ingredients.
Yeah.
Mhm. So choose any two.
The
First and third. So let's say we have electricity and we have motion. So if you're running electricity through a wire, right? So it's moving electrical field, we are going to get magnetism. And that is how we get an electromagnet, right? If we have our wire and we run electricity through this, it becomes magnetic. So running electricity through a wire creates a magnetic field. And this is a very important concept. Running electricity through a wire creates a magnetic field. We are going to see this come into play in just a few slides when we talk about, well, do we talk about transformers? We'll kind of talk about transformers, I think, right? So yes, make sure you do understand that electricity and motion induce a magnetic field, because that's going to be very important to what's coming up.
You said they produce what?
Electricity and motion will induce a magnetic
Oh,
field.
induce.
Right. So, types of current. We have AC, we have DC, right? Much like the band, AC, DC. Okay. Okay, probably too old for you guys.
I got it.
I'm joking, I'm not that old myself. Okay, so DC, direct current, right? This is what Edison liked. Current only flows in one direction. This is what we normally see with batteries. This is what we normally see with things like, charging your phone, right? You only want the electric current to flow in one direction. alternating current, the current flows back and forth, right? You kind of saw that here, right? You see the arrow going back and forth, right? On that voltage here. So alternating current, our current flows one way and then the other. It goes one way and then the other, back and forth. It wiggles back and forth. Okay. How fast it wiggles back and forth is a frequency. And so in the US, our electricity alternates at 60 hertz. Okay. You go to Europe or something, their electricity alternates at 50 hertz. So you can't just use the same appliances here in the US over in Europe, right? You need an adapter. But you need to be able to adapt your appliance from 60 hertz to 50 hertz. And you may find that your appliance also works slightly differently, right? It may not work as well or as strongly because the alternating current is slightly slower. Okay. So here in the US, our alternating current just goes back and forth like this, 60 times a second. Alternating current is useful because it allows a current to travel long distances. So if the power plant wants to get electricity from itself to your house, it can't use direct current. This does not have enough reach to reach your house, right? If it's traveling miles and miles and miles, we use alternating current to let the current travel those long distances. Yes, Jay?
So direct current would be more ideal for like a strong energy source that's like close to its target,
Correct.
whereas like AC is just capable of transporting that energy. Like it's, how does that work then? Is it just like electron rich like wire that's like just doing this the whole way, like every?
The electron charge goes, yep, and then
Okay, so they're like all communicating at the same time. Okay.
it's kind of like water in a pipe, right?
Yeah.
If you push water in one end, right? It's not like the water needs to phone its friend all the way to the other end. Okay, time for you to move, right? Just you push here, it comes off that side, right? But in this case, we're just going push, 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 back and forth.
Do you know why they use 50 hertz?
That I do not. I think it was because it was easier to do calculations with. I believe that's the reason.
We're always making things complicated. Imperial system. Good old matrix.
Alright. And so, that brings us back to induction. But now, we're going to be talking about induction with these solenoids. Right? So, let's say we've got two solenoids here, right? On this solenoid, we are running an electric current. So we run an electric current down through this wire like this, right? Comes in this way, comes out that way. When we run an electric current through this, what do we create? We create a magnetic field. Very good, right? So we've induced a magnetic field in this solenoid. This magnetic field, right, here are the green lines of flux, right? These lines of flux, as you can see, travel out to the second solenoid. So now you've got a moving magnetic field in a solenoid. What do you think is going to happen over here in this wire?
That magnetic field is also moving, but more faster.
So if you have a magnetic field, so over here we had electricity, we had motion, that created a magnetic field. Over here we have a magnetic field and motion. What does that create? Electricity, right? Our three ingredients. Motion and magnetic field gives us electricity in this side. So we can actually take electricity from one wire and create electricity in a second wire without them ever touching. This is mutual induction. You can have two separate wires. One wire does not have an electrical source at all, but you can create a current inside that wire through mutual induction. An electric current in one wire can create or induce an electric current in a second wire. Right? In this case, we do need solenoids. We need these coils to do so.
Is it the same exact electrical value in the other wire, or is it a little weaker?
It is going to be the same provided that the number of turns are the same. As long as they have the same number of loops, you will have the same voltage in the same amperage.
So the second, the self-induction, it has to have like a changing, is that good?
Yes, so now let's talk about self-induction.
Oh, so we already talked about it, my bad.
Because here inside this wire, right, we have this created magnetic field now. Right, so this magnetic field is currently existing. Now let's say that we want to reverse the direction of the current. This magnetic field that exists is for current going one way. We try and create a current going the opposite direction now, right? So this existing magnetic field acts almost like friction, acts as an opposing force to our new current, our new direction that we want our current to flow in. Right? And so self-induction is when our current, our existing or previous current in the coil, right, created this magnetic field, and now it opposes a change in that current. Right? It's like electrical friction. It opposes the change. Or it's kind of like momentum, right? It opposes the change. You push something one way and now you want to push it the opposite way. You need to work against that force first.
So what changed the original current? Was it the magnetic force, or was it the new current or electrical current that we applied?
Correct. So imagine it's an alternating current, right?
Mm-hmm.
If it's alternating, it's going to go this way half the time, and this way the other half the time.
Mm-hmm.
So it's going this way, it creates a magnetic field. It now wants to go this way, but it needs to work against the magnetic field that has already been created, right?
Mm-hmm.
And then, after it's traveling this way and we create a new magnetic field, it wants to switch again and go back this way. And once again, it has to work its way through, work its way against that existing field, that existing current, right? So that's why, right, it opposes the current, right? We want to try and go this way, but the magnetic field is pushing us in this way instead.
What's the purpose of that? Do we utilize the lost, the energy and friction, or?
So this is just a property of magnetism, right? Sometimes it's useful, sometimes it's not. But this is just a property of magnetism, that we have this sort of electrical friction inside our wires when we want to switch things back and forth. So we will see how self-induction can be useful when we talk about transformers. So we do have a use for this. Okay. It's okay, guys, it's okay. So transformers, right? Not the robots in disguise. These transformers are electrical transformers that change properties of your current. So we use transformers to either increase or decrease voltage and current using induction, right? Using this idea of, well, we've got two wires, right? So I've got one voltage, one current in one wire. I'm going to create a different voltage and a different current in this second wire, right? And the way we do that is through induction. Okay. If we want to make this even more effective, right, we can throw in this iron core in between the two wires, but it's not necessary. It just helps to guide the lines of flux to make it more efficient. But the idea here is, okay, primary coil, we've got our alternating current. We are going to induce an alternating current in our secondary coil, right? So power comes in here, we have our current, we have our voltage, we have a magnetic field. That is going to influence this wire over here to also have a voltage, a current, and a magnetic field. And these two do not necessarily need to match. We are able to transform our voltage and current, right? That's why it's called a transformer. We transform it.
Go back and change.
Oh, sorry?
So it transformed the magnetic field.
So we're going to transform the strength of the voltage, or we're going to transform the strength of the current. So we're either going to change the volts or the amps. Or actually, I'm sorry, we're going to end up changing both. Right? Because if one goes up, the other one is going to go down. So let's take a look at how this works. If we end up increasing the voltage in the secondary side, that is our step-up transformer. If we decrease voltage, that is our step-down. So step-up and step-down refers to voltage. Okay? So if we have voltage coming in on this side, primary side, right, so this is our power plant somewhere all the way down here. It's giving us 110, 120 volts. Right. Over here on the secondary side, right, we are inducing a current here. We're going to get higher voltage. What do you notice about these two solenoids?
There's more coils on that side.
That's right, there's more coils on this side. So the side with more coils is going to be the side with the higher voltage. If we look at our step down, high voltage coming in, low voltage coming out. Once again, what do you notice about the number of coils?
There's less.
Right, less coils on the secondary side, more on the primary side, which has the higher voltage, right? So when we're talking about transformers, which side is going to have the higher voltage? The side with more what? Coils. The side with more coils. Very good. Okay. The side where the voltage is coming from, that is our primary side. Right, so primary has nothing to do with the number of coils. It's just where the power is starting from. Right, secondary side is where all this energy is going. Okay, so primary, secondary, it doesn't tell you anything about the numbers, right? Big number, small number, doesn't have anything to do with that. It's just energy comes in, energy goes out. Okay, what tells you about the number of coils is either step up or step down. If you have more coils on the primary side, what is that?
Increase. Step up.
More coils on the primary side?
Step down.
Step down. As more coils on the primary means higher voltage to start with, lower voltage to end with. So you're going from high to low, you're stepping down.
So a transformer with a primary side that has less coils and a secondary side that has more coils is a step up.
Correct.
Primary and one with a primary side that has more coils and a secondary side that has less coils is a step down.
Correct.
Okay.
Yes, Jay.
I don't know if I'm getting ahead of myself again, but like we learned something else like that started with was it transistors or something like that? Transistors?
Did you learn anything like
I don't know if that's like, is that in the electrical current or is that no? Is
Oh,
that,
unless you're talking about like the thin film transistors.
oh, is that
discussed in
that's just
chapter
the
10.
TFT?
TFTs,
Oh,
yeah.
dude.
Alright, so of course with transformers we're not creating stuff out of nowhere, right? If the voltage goes up, right, we're not just creating extra electricity out of nowhere. There has to be something else that goes down to balance it out. Right? Because you can't create or destroy things in science, right? Things have to stay equal. So the power in your circuit is staying equal. If the voltage is going up, something else has to be going down. And that is the current. So when voltage goes up, current goes down. with your transformers, right? If the current is going up, then that means the voltage is going down. Right? Current and voltage travel in opposite directions with your transformers. Okay. In addition, right, don't forget that if you have more coils on the secondary side that step up, more on the primary side that is step down. And so we can use this to actually calculate exactly what is going to happen based on the number of turns in that solenoid, in that transformer. So remember, right? Power is voltage times current. The power on both sides of your transformer has to be the same. Okay? So over here, we have our transformer law. This is an equation you do need to know. Okay? You will need to know how to use this for voltage. In this case, voltage is directly proportional to the number of coils, right? We saw more coils, more voltage. Okay, so just, right, it's directly proportional, right? Goes straight across, primary, primary, secondary, secondary. Doesn't matter which one's on top, doesn't matter which one's on bottom, just know that it is directly proportional. So let's use this. Or sorry, yes. So let's talk about current then. Because we said current is opposite of voltage, right? If voltage goes up, current goes down. Mm-hmm. So because voltage is directly proportional, current is inversely proportional, which means our transformer law for current is this. Now notice that the primaries are on opposite ends, and the secondaries are opposite to each other, right? Now instead of being straight across, you have this crisscross. Okay? So, voltage, current, right? Voltage, current. You do need to know both of these.
So the top one's voltage, the bottommost is current?
Correct.
What's the one in the middle?
This here shows you how we got from voltage to current. Right, I didn't make up the current equation from thin air. I'm showing you how this came about. Because voltage and current are inverse, that's what we said. So that's why we're able to get this equation here. But the two equations that you should know are the top one and the bottom one. Those are your keys.
So the NS and P is the same.
So what do you think NS stands for?
The number of
Coils.
Number of coils?
in the secondary.
Good. S for secondary side, right? What about NP? Good. Number of coils on the primary side. What is IP? I is current.
Primary.
P is primary. What is VS?
Voltage.
Voltage. Secondary. What is IS?
Current secondary.
Current. Secondary. What is VP?
Voltage primary.
Voltage. Primary. Yes, Charles.
So the first, one is just saying that secondary voltage is directly proportional to secondary coil, number of coils.
So we're not going to talk about it in terms of secondary or primary.
Okay.
When we talk about
So
proportional.
voltage and coils are directly proportional.
Correct.
And current and voltage is is inversely proportional.
Correct.
And current and number of coils is inversely proportional.
Correct.
Okay.
Okay. So the part that we've all been waiting for ever since you saw those equations.
The
Let's do some math.
end.
Don't worry. This is once you do see this, you'll actually find out this is pretty straightforward, it's pretty simple math. We have a transformer, 150 turns on the primary side, 300 turns on the secondary side. Primary side has 120 volts and 5 amps of current. So, first of all, just looking at the number of turns. How many turns on the primary?
150.
150.
Oh,
Anyone else?
Was that too slow?
All right, come on, everyone. How many turns on the primary
150.
side?
150.
Good. How many turns on the secondary side?
300.
Which side has more?
Secondary.
So are we going from low to high or from high to low?
We're going low to high.
Low to high, so what do you call that?
Step up.
Yeah.
Step up, right?
I like that.
You got a step up transformer. Okay, and why is this a step up?
Because you're
We
going
went from
from
150 to 300.
That's right, we're going from low to high, right? Secondary side has more turns. Very good. All right. So, now that we know this is a step up transformer, right? When we get our answer, do you expect our answer to be bigger or smaller than 120 volts?
bigger,
Why bigger?
because they're directly proportional.
Correct, right? Step up transformer, so we're expecting this to go up in terms of voltage, right? It's directly proportional to the turns, right? Turns is going up, voltage is going up. So what is the voltage on the secondary side?
240 volts, I believe.
So how do we set this up? What is our equation?
VP 120 over VS, then NP 150 over NS 300.
Okay. All right. So, yep, you can do it that way, right? You can put the P's on top, S's on bottom, doesn't matter. As long as they are on the same side, right? Here and here. Great, so let's try and fill this in. What is our VS?
120.
We don't
No,
know.
we don't know.
That's
Yeah.
right. That's what we're looking for. Good. So we'll leave this alone for now. What's our VP?
120.
Okay, 120. Where do you see that?
Right there.
Ah, right here, right? 120. Primary side has 120 volts.
Mhm.
What is our NS? 300, right? Number of turns on the secondary side. What is our NP?
150.
150 turns on the primary side. So, right? We throw all of this in here, and when we stick this into the equation, what do we get?
240.
That's right. We get 240. You just cross multiply. Or, if you pay attention to these numbers, right? 150 to 300.
2.
What did we multiply by? 2.
2, yeah.
So 120 to 240, you also multiply by 2.
Oh, that's a simple class A. I like that.
So that's a shortcut.
Yeah.
Right, you just look at your terms, primary and secondary, figure out what number you multiplied by. You multiply by 2. So then you multiply your voltage by the same number. 120 times 2 gives you 240. So that's a shortcut you can use. Usually the registry will use simple numbers like this. Right, you're not going to have them multiplied by 1.476 or something. Usually it's going to be straightforward. Yes, Carlo. Question? No? Okay. Oh, good. 240 volts. Let's try another one. This time, right, same numbers, but what are we looking for this time?
The current.
Current. So do we expect current to be bigger or smaller than 5?
Smaller,
Why?
because it's inversely
Right.
proportional.
That's right. Current is inverse, right? So if it's step up on voltage, we're going down with our current instead. Okay. So what is our equation for current?
It is 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 equal to VP.
S over.
Good. As long as they're opposites, right? It's perfectly fine. So what is IP? 5. What is IS?
2.5.
Don't know. What is NS? 300. Good. be 150. Very good. Right, so we've got our numbers here. We throw them into the equation. And so when you cross multiply, what do we get?
1,500. I did my math.
So it also works the opposite way. If you know that's 2, you just divide 5 by 2 and you're gonna get the answer.
Right, so just like how we had the shortcut for voltage, we can do something similar for current, right? You multiply it by 2 here, so you do the opposite because it's inverse for current. So you have your 5, instead of multiplying by 2, this time we divide by 2. So 5 divided by 2 gives you your 2.5. Okay. So if you want to use the shortcut, you're free to do so. If you're gonna do it out the full way, just to make sure you don't make any mistakes, right? Feel free to do so. Main thing though is always check your answer logically, right? Once you have your answer, come back and ask yourself, all right, I have a number. Did it go the direction I expected it to? Earlier, which direction did we say we expected this to go? Right, we expected us to be smaller than 5, right? Is this smaller than 5? Yes, so it makes logical sense, right? If we got an answer like 10, then we know, uh-oh, I must have gone the wrong direction. Maybe I used the wrong equation, or I flipped my variable somehow. And then you can go back and fix your calculations. Okay. It's also a fast way to eliminate answers on a multiple choice question. If you know that it's supposed to be smaller than 5, you can eliminate any answer that's bigger than 5, right? Narrow things down, make things easy for you. That's the beauty of multiple choice. Okay, let's see how much further I have. Okay, just a little bit more. Almost there. Okay, so auto transformer. Notice.
Autobots.
No, then it's 11:45.
It does.
All right, it does. Yes. Okay, how many coils do you see here? Or sorry, how many solenoids do you see here? Only a single solenoid, right? However, this is also a transformer. So a transformer is only one winding, only one solenoid is an auto transformer. Auto means self, right? So by itself, with its single winding, right, its single set of coils, it is able to do the job of a transformer. So over here we have primary side, over here we have secondary side. Notice that there are these little things coming off the wire, right? These things coming off the wire are called taps. These are access points where we can determine the secondary side, right? So if there's 20 coils on the primary side, on the secondary side, we can actually choose how many coils we want. Do we want like 15 coils, 10 coils, 8 coils, 5 coils, right? You actually have the option now to choose how many coils you're dealing with.
So you just put a tap on the ones that you want.
Correct. So an auto transformer is a transformer where you can vary, where you can change what the secondary side looks like. Right? Our previous transformers were fixed. Right? Our previous transformers with primary side, secondary side, there was this number of coils on one side, this number on the other. You can't change it. But with the auto transformer, you are allowed to change things.
So what was the auto transformer? You can change. You're able to change it.
You're able to change the number of coils on the secondary side. So, why is this important? Well, how do you think your KVP selector works? When you're changing KVP at the console, what do you think is actually going on in the background? This, right? When you're doing your KVP, how are you able to change your voltage? You're changing your voltage using a transformer. You have only one voltage coming in from the wall plug, but you can get all these different voltages with your machine because you're using a transformer to create these different voltages. And specifically, you're using an auto transformer because that lets you choose your different KVP values. Does that make sense? Right? To me, that's kind of exciting. That's kind of cool. And same thing for your mass, right? How are you able to change the current of your tube? Right? You have only a certain current coming in from the wall. You change the current, once again, using taps, right? So, autotransformer plays a key role in KVP selection. Now, the math for an autotransformer is exactly the same as a normal transformer. So, let's try this out. How many coils on the primary side? 100. How many on the secondary side? 80. Did it go up or down? So what kind of transformer is this? Good, we have a step-down transformer, right? More coils on the primary side, less on the secondary side. Okay, what is the voltage on the secondary side? We're using the exact same transformer equation, right? What is the equation with voltage? Good. So in Mamsi's case, she's putting the P's on the top, the S's on the bottom, right? You can also put the S's on top, P's on the bottom, doesn't matter. It's all the same. So what is VS?
80.
We don't know yet.
No, yeah, that.
What is VP?
120.
120. What is NS?
80.
80. Right, secondary side. What is NP?
100.
100. Very good. So we take these, we throw these into our equation, and when we do this, what do we get? Right, so we do our little cross multiplication, and if we did this correctly, we should end up with 96 volts. Is 96 bigger or smaller than 120? Smaller. Does that make sense for a step-down transformer? Yes, it does. Okay, so that answer looks good. All right. Over here, we have now changed our secondary side so that we only have 60 windings now, right? We changed the taps, so instead of 80, we went down to 60. Right? Still asking about voltage, so the only thing that changed here is the secondary side, right? The number of turns on the secondary side. Now, if you try and do this, what do we get for our voltage?
The last one was 96, right?
72.
This is 72. Very good job. Great job, everyone. So, 72 volts. Earlier, like Jay said, it was 96. So, bigger or smaller than 96? Does that make sense if we went down on our windings?
Bless you.
It does, right? Fewer windings, lower voltage, right? Voltage is connected to the number of turns, the number of windings. All right, and that's it.
Yes.
We are done.
Good job, Mr. Phung.
Good job. Good job, everyone.
Good job, Mr. Phung.